Hello, Physics 1 students. Um, this is a video describing how to understand the kinetic energy, so energy of motion, but we want to focus on rotational motion. And we're going to talk about rigid objects only. So if you're thinking about it, we're talking about a frozen pizza dough, not defrosted pizza dough. So we're not going to allow the objects to deform as they rotate. And we're going to talk about rotation about a fixed axis. Okay, so what we will imagine is there's some fixed axis and the object or objects will rotate around that with some angular velocity omega. All right, so let's kind of unpack various assumptions we can make, or that we have made, or we're going to make. Rigid, well, what that really implies is that every point kind of moves together around this axis. And in particular, that's going to mean that omega, alpha, and also delta theta are the same for all points in the object. Okay, so the velocity may not be the same at every point, but the angular velocity will be the same at every point. So think about it, if there's a merry-go-round and let's see, oh, I heard that Abby doesn't like it when I make her the victim. So we'll have her be the instigator. So Abby is going to spin the merry-go-round, and we're going to have Ryan holding on for dear life as Abby spins Ryan around in the merry-go-round. So what we notice is, let's imagine in some amount of time, you'll notice that Ryan's head travels this far and his feet will travel this far, so that at a later moment in time, Ryan has moved around and his entire body has spun around. And each point in his body has traveled through the same angle. So it's the same angle theta for each point along Ryan's body. So therefore, all points in his body experience the same change in angle, and similarly, same omega and same alpha. However, his feet have traveled a much longer distance than his head. So the velocity, the linear velocity of his feet must be greater than the linear velocity of Ryan's head, even with the same angular change. So that's just the first observation. That being said, these are motions, the little chunks of a person, little pieces of Ryan, his feet and his shoes and whatever, they're moving with some velocity, so they have kinetic energy. So rotational motion is motion. Therefore, we expect kinetic energy associated with rotations. I'm just going to tell you right now, if you haven't watched our first video on using the moment of inertia or defining the moment of inertia, go stop this video and go back and watch that one, because we're going to use that and we're going to see that it emerges from the equations here. So, okay, so we want to talk about objects that are rotating. Let's start simply. Let's imagine we have a point mass. Think of it as a little marble or something like that. And we're going to imagine we have an axis of rotation, which is fixed. We're going to have a point mass here. And we're going to assume it rigidly rotates around this axis. So what you could imagine is that there is an infinitely thin wire or something holding it in place at a fixed radius. So this is the radius, not with respect to some coordinate system, but with respect to the axis of rotation. Just to remind myself of that fact, I like to write this as r perpendicular, because this is the perpendicular distance from the axis of rotation over to my mass. And my mass is going to rotate around with some angular velocity omega. Well, if you were to trace out the path taken by this mass, you would actually see, if I went to kind of a bird's eye view, so I put this from the top, what I would find is that here's the center, here's the axis, and then I have my mass, and I would find that the mass follows a circular path, and the distance to the center is always r perpendicular the whole way along. So the radius of this path would be r perpendicular. So from the top down, we kind of see this circular motion. This little chunk follows a circular motion trajectory about the center of the object, or sorry, about the central axis of rotation. Well, because it's circular motion, we immediately can relate angular changes to linear quantities. So for instance, we can say that r times omega equals v tangent, and we can say, well, that's really the one I really want to use. So I can relate, oh, sorry, that's in general. In this particular case, I want to specialize it to r perpendicular. So I can say that's r perpendicular times omega equals v tangent. All right, so now, well, this is just a point mass. It's moving, it has some velocity, and it's only in one direction. So there's no radial motion. So I can just write down the kinetic energy for this mass. And this is simply 1/2 the mass times its velocity vector squared, but that's just going to be the one component that is actually not zero, because the radial velocity is 0. And then I can recast this in terms of angular quantities. So I can rewrite this as 1/2 the mass times r perpendicular squared times omega squared. All right, so if you haven't watched the video on moments of inertia, this will just look like some expression, some random expression. But if you have, hopefully you can recognize this as the mass times the radius perpendicular squared is in fact the moment of inertia of a point mass. And so we get an equation, at least for a point mass. We find that the kinetic energy of a point mass, a rotating point mass, I'll just leave it like that, equals 1/2 I for a point mass times omega squared. So when expressed in rotational quantities, this is what I have. The linear version of kinetic energy is 1/2 m v squared. And we immediately see, at least for point masses, and we're going to see that this is true more generally, that there's a sort of dictionary between rotational expressions and linear expressions where you relate omega can go back and forth with velocity, and I can go back and forth with mass. So just remember that. It's kind of a good thing to just know when solving problems. All right, what about more general shapes, more complicated situations? I think I'm going to need more room, so I'm going to go to another page. So for a more complicated shape, so let's imagine I've got some axis of rotation, and let's imagine I've got some random lumpy shape. but it's rigid. And so this rigid shape is rotating around this axis with some angular velocity omega. How can we estimate the kinetic energy in this contained in this object as it rotates? Well, the key is to play Legos. So break it apart. Think of it as being built out of a whole bunch of little point masses. And what we're going to do is then say that the kinetic energy of the total object is the sum of all the individual kinetic energies. Each little chunk would have its own R perpendicular. So I'll call this R perpendicular 1. This could be R perpendicular 2. For the third one, you could have R perpendicular 3. Or in general, each piece has their own perpendicular distance, R perpendicular I. And, you know, there's nothing saying that they have to all have the same mass, so they could each have their own mass, mi. So we could just write down the kinetic energy total. And this is going to be rotational kinetic energy because it's associated with a rotation about a fixed axis, not motion of the kind of bulk motion of the center of the how do I say this? Not some overall motion that's linear. We're talking about a rotational motion. So we're going to call this a rotational kinetic energy. And I could just say, well, that's just going to be the sum over all the little pieces of all their separate kinetic energies. So that's going to be, there's going to be a 1/2 out front, the mass of each one times the velocity of, and it would be the velocity tangent to, each one follows a circular path, but that's okay. And so they would each have their own tangential velocity squared. But because, you know, if I take a bird's eye view, each one of these little pieces follows a circular path. So if I kind of draw my axis of rotation, I have my irregular object, and I have these little masses. And I would see that each one of these is going to have a circular path, around the axis of rotation. Okay, so for each one of these, I can relate the tangential velocity to angular quantities. So I could write this as one-half sum over mi, and I would say, well, remember the tangential velocity is r times omega, so I could write that as r perpendicular I times omega I squared, and I would sum over I for all the little pieces of mass. But if it's a rigid shape, then omega I is the same for all of them. So omega is actually, I labeled it with an I, but actually it would be the same number for every chunk. So it's a constant, and you could actually pull it out of the summation symbol. All right, so now we have to perform this sum over each little chunk, the mass of each chunk, times the perpendicular distance associated with each chunk. And how many chunks are there? Well, really, I should imagine taking a limit, so you have an infinite number of tiny little pieces. So the sum is going to become an integral. So we end up with the formula for the rotational kinetic energy about a fixed axis as 1/2 the sum times this quantity. The sum becomes an integral dm of r perpendicular squared times omega squared. And this is nothing other than the moment of inertia, not for a point now, but for the shape about the appropriate axis. So the formula I highlighted for a point mass immediately generalizes to the following. So that the kinetic energy of rotation equals 1/2 I omega squared, and that's analogous to the linear kinetic energy, which would be 1/2 mv squared. And this dictionary that I boxed in is going to be helpful. It's a helpful mnemonic to kind of remember that you can kind of, if you understand normal kinetic energy or the linear quantities, then there's a dictionary that immediately takes you to their angular analogs. Let's see how this plays out in practice. So let's imagine that we have an object that rolls without slipping. So we're going to take this to be a solid disk. If you remember, for a solid disk, the moment of inertia has the following formula. It's equal to 1/2 the mass of the disk times the radius of the disk squared. So what I would like to know is how much energy is needed for a let's say a 1 kilogram disk to have a velocity in the x direction equal to 3 meters per second. So we want this disk to, the center of this disk to move at 3 meters per second, let's say to the right. And it has a mass of 1 kilogram. I would like to know how much energy would you have to put into that to make it happen? So to analyze this, we have to think about the motion, and we see that there are two components to the motion. We have translational motion, plus we have rotational motion about the center of the wheel. So it's moving in two ways. That's okay. That just represents two forms of motion, 2 degrees of freedom, 2 ways to store energy or to have energy. So the energy associated with this shape, which would just be kinetic energy, we don't have any friction or work or anything. Well, we have friction because it rolls without slipping, but we don't have any work right now. So kinetic energy only, and there are 2 ways that it's moving, translational and rotational. So we're just going to have a kinetic energy. The total kinetic energy is a sum of the translational plus the kinetic energy associated with rotations. And then we just follow our nose and plug in formulas. So the formula for kinetic energy of translations is 1/2 the mass times the velocity of the center of mass squared, plus the rotational kinetic energy, which is 1/2 the mass, 1/2 I times omega squared. Okay, so the numbers I know are mass and velocity, and I have a formula for a moment of inertia. Oh, I have to give you a radius. Sorry, I should have done that. Let's say I have a radius of 0.1 meters, so 10 centimeters. I should have said that. To evaluate this formula, though, I need to know omega. So think a second. How could you find omega? While you're thinking about that, I'm just going to wait here, and I'm just going to casually not make any suggestions. I'm just going to doodle here while you're thinking about it. How could you relate omega to other quantities? Oh yeah, no slipping, right? The last video described how you can use no slipping assumptions to solve problems. Because we have no slipping, we know that the velocity in the x direction of the center of the wheel equals, up to a minus sign, potentially, r times omega. And then you have to look at it. If it rotates clockwise, then the object moves in the positive x direction. So that means a negative rotation gives you positive motion. And so you need an extra minus sign to make the equation work out. Now, it's not going to matter for kinetic energy, but it's just good practice because there are going to be problems where the minus sign does matter. Here, it's going to be squared, so we don't care. Omega then equals minus velocity of the center over r. So we can just plug everything in. Look what happens. It's kind of an interesting fact. Well, okay. So let's write down our formula for the kinetic energy. Total. That's 1/2 the mass times the velocity squared. That's the velocity of the center squared. Plus 1/2 I omega squared. So let's just start. What we know, I equals 1/2 m times r squared. So I can rewrite this. I itself has an extra factor of 1/2. Remember, every shape will have a different formula. Times the mass times the radius squared times omega squared. But omega can be written as v of the center over r squared. So for this shape, because it's rolling on the rim and there's only one length scale in the problem, you actually get a nice cancellation that occurs. And for simple shapes, that'll happen in simple configurations. So you actually didn't need to know the radius. It wouldn't matter. And so we actually get a final expression, which is 1/2 coming from here, plus 1/2 of 1/2 m times the velocity of the center of the object squared equals 3/4 the mass times the velocity of the center squared. And if I plug in numbers now, I said, so that's going to be 0.75. I said the mass was 1 kilogram. And I said the velocity was, I believe, 3. Let's go back and check here. Yes. And so you get 0.75 times 9. So 90% of 0.75. I don't know, 0.75 minus 0.075. So it'd be about 0.6. 75, I believe. Shift the decimal point one spot. I think I did that right. Just doing it in my head. Joules. Oh. Okay. Notice, because we have extra degrees of freedom, which take energy to activate, to involve, the total kinetic energy now is bigger than it would have been if the object just slid along the table, or if you had just, frictionless sliding, you wouldn't trigger any rotations. It would just kind of rigidly or kind of steadily move across the table, and you would only have the linear term. But now, because it can both slide and rotate, you have to add them together to get the total kinetic energy. All right, so that's an example using rotational kinetic energy. I just want to highlight the formulas. In general, kinetic energy, the total kinetic energy is going to now be the sum of translational plus rotational. And the formula for the translational portion is going to be the familiar one. One half mv squared. And that really should be a vector dot product with itself, but usually in these problems we only have one thing going on at a time. And then we have the rotational portion, and that equals 1/2 the moment of inertia about the axis which is it's rotating about. So you have to look at the situation and figure out what is the appropriate I to use, times omega squared. And then when we have no slipping, if you have this, then use it. If you forget this condition, the problems will become usually impossible. Like, you don't have enough information to solve it otherwise. Okay, so that's rotational kinetic energy, and we saw the moment of inertia make an appearance. In the next video, I'm going to talk about how to find moments of inertia of more complicated shapes. And then after we have that, we will talk about torques. See you next time.